Hello, everybody. Welcome to the theory session. So good morning, good afternoon, good evening, depending on where in the world you are. So we've got a great bunch of 6 papers today. My name is Tamara Munzner from University of British Columbia, and I will be your session chair. We're going to have a mix of groups, a mix of people, a mix of methods. So hang on to your hats. It's going to be fabulous. Enabling deeper understanding of data using VR, presented by Benjamin Lee. And let me point out that this was a best paper honorable mention. So let's roll that video.
Hello everyone, my name is Benjamin Lee, and I'll be presenting our work on data visualization, which is a technique we propose to help users better understand certain types of data using virtual reality head-mounted displays. Narrative visualization has become increasingly commonplace as online journalists and storytellers seek to communicate insights and data. Coined by Siegler and Hare in 2010, they describe 7 different genres used in these stories, which have been then extended upon by researchers. Since then, use of virtual and augmented reality technology has become increasingly common for data visualization and analytics, also known as immersive analytics. It makes sense then to ask how it can be used for narrative visualization and data understanding. Existing research into immersive data-driven storytelling has been limited, however. For instance, works by Pistorius and Thomas on the left, and Vande and colleagues on the right, result in using flat two-dimensional panels with conventional data visualizations, and do not take advantage of the inherent properties of immersive technologies. One such property is the ability to provide very visceral experiences to users, such as simulating a series of shocking events in immersive journalism, or instilling a sense of vertigo when at a seemingly great height. When considering how this may apply for information visualization, we are most inspired by a VR piece from the Wall Street Journal, which uses the Nasdaq's price-to-earnings ratio as a roller coaster track. The reader rides this track from one end to the other, where they viscerally experience a sudden drop in the Nasdaq as a literal roller coaster drop. This notion of taking data and mapping it to a visual experience was something we wanted to capture. Looking more broadly, conventional data visualization relies on abstraction and transformations to translate raw data into abstract visual representations. This process causes the connection to the underlying ground truth to be lost, however, as points and shapes are very different to what the data truly means in reality. By using immersive technologies to enable visual experiences, we can instead simply show the data as is, with little to no abstraction or transformation involved. This lets us accurately represent the ground truth of what the data means in reality, and may provide a more proper understanding as a result. We formalize this idea in what we call data visualizations, which we loosely define as data-driven experiences which evoke visual feelings within a user to facilitate intuitive understanding of physical measurements and quantities. So for example, imagine being told that the Eiffel Tower was 324 meters tall. Trying to understand what exactly this means or even what it looks like is quite challenging, even when you are told that it is 3.5 times the height of the Statue of Liberty. With data visualization and virtual reality, it becomes possible to simply just show the Eiffel Tower at its true scale, providing users a visual sense of how tall it actually is, or in other words, the ground truth of the data. This technique shares similarities with others, the most prevalent being concrete scales. This, however, involves the building of mental models of scale, a process which we skip altogether with visualization. Another technique is data physicalization, which maps data to tangible objects in our 3D world. However, physicalization oftentimes uses abstract visualization idioms, and fabrication can be expensive and time-consuming, which visualization with VR avoids altogether. To test and explore the concept of data visualization, we developed 6 VR prototypes as design probes using the Unity 3D game engine. Each was designed to specifically communicate a certain type of data, and was based on an existing data visualization or narrative visualization. These also implicitly covered 2 categories: data types which were straightforward to translate into and perceive in VR, and those which are a lot harder to do so. I will now play an excerpt from our supplemental video which showcases these prototypes. Based on the aforementioned example and the One Race Every Medalist Ever piece, we recreate its video and 3D models. Users can replay the race at will and watch it from any angle they wish to viscerally witness the actual speed of the runners, something not otherwise possible in real life. Similar to the previous design probe, Bob Beeman's long Olympic shadow showcases the difference in distance jumped between the Olympic medalists. Instead of relying on the basketball three-point line as a concrete scale, however, users can directly see the distance that each one jumped for themselves in a one-to-one scale with reality. We recreate the popular size diagram of skyscrapers to explore how height can be viscerally experienced. As compared to a static viewpoint, users can judge for themselves the large scale of these structures from a wide range of perspectives, such as from below, from the top of a building, or from a long distance away. There exist many examples which put into perspective the enormous scale of the solar system by rescaling it into graspable ranges. To explore the effects of this rescaling on visceralization, we implement a related example, fitting all planets between the Earth and the Moon, where VIA allows users to view these scaled down planets from a wider range of angles. To explore quantities, we recreated a snippet of the Hong Kong protests to understand how counts of discrete objects, in this case people, can be experienced. This includes being in the crowd itself, or flying above it in a helicopter-like fashion. Finally, we looked at representing abstract quantities as visceral experiences by using the concrete scales principle with the US depth. Users can directly experience the sheer scale of the depth as if it was physically there in front of them to see. As is the nature of presenting virtual reality applications, we invite you to try them for yourselves to properly experience these prototypes. They are in a public GitHub repository as shown on the screen right now, and the link is also available in the manuscript. Using these prototypes, we as the authors critically reflect on them in order to better explore and characterize data visualization. We had also invited 12 participants to try these data visualizations and give feedback on them, but we had only limited them to the Olympic sprinter, skyscrapers, and US depth prototypes due to time restrictions. We ran this as a qualitative study as a way to further expand our original critical reflection, and we elicited responses through a questionnaire which they answered after trying each prototype, and a semi-structured interview at the end of each session. For the purposes of this presentation, I summarized our findings from both reflection and user feedback together based around the following topics: the importance of visual sensations for understanding the presented phenomena and underlying data, how well the presented phenomena could be perceived, how the virtuality of VR could be leveraged, how important realism is, how useful annotations are, and lastly, the challenges in using complex data types for visualization, such as money. Please see the manuscript for a more detailed breakdown of both the critical reflection and user feedback sessions separately. First of all, despite being its namesake, many participants stated that the feeling of visual sensations, such as having sprinters directly run past them, or the feeling of vertigo at great height, was not required to understand the underlying data. In contrast, however, many commented that the innate emotional responses triggered by such events makes the overall experience feel more authentic and therefore convincing. When it comes to actually viewing the visualizations, it was clear that there was a perceptual sweet spot that works well for visualization. This is typically of human-scale phenomena such as the Olympic sprinters, as they are the easiest to fully see, grasp, and comprehend. This did show its limits, however. For example, all skyscrapers did just look tall past a certain height when looking at ground level, making it difficult to discern between any differences between them, and therefore minimizing its usefulness. There were, however, many different ways to accommodate this issue by leveraging the virtuality of VR, enabling new techniques that are not otherwise possible in real life. For example, users can instead fly to the tops of each skyscraper to compare its height relative to the others for themselves. This allows for novel understanding and insights to be gained where not otherwise possible, a notion that was confirmed by some participants. However, they also stated that this freedom to explore made it more time-consuming and difficult to figure out what they should be looking at in the first place. To explore the function of realistic rendering in visualization, we had replaced the presented phenomena with low-fidelity versions, such as human-sized blocks instead of humanoid sprinters. From our reflection and user feedback, it was clear that the lack of realism did not impact the perceived sense of speed, scale, etc., as these numerical aspects were still present. As participants suggested though, a baseline level of realism is important in order to establish the context of what is being portrayed, and also makes the entire experience just more enjoyable. We had also explored the use of annotations in our prototypes, as you see on the screen right now. While we had thought that these were distracting during our initial critical reflection, participants found them to be incredibly useful to provide much needed numerical context to what they were looking at. For example, They could tell that Usain Bolt was fast, but only with the annotations could they tell that he was 10.38 meters per second fast. What was interesting though is that learning these numerical values was not the intended goal of our participants, as they only support the actual goal of seeing and experiencing the ground truth representations. Lastly, it is apparent that data visualization works best when there is a one-to-one mapping from the data to the visualization. That is, being able to represent the ground truth of what the data is, such as with the skyscrapers and splinters, without any transformations or alterations. Some cases where this was not possible was in the US depth and solar system prototypes. In both of these, some intermediary transformation had to be applied. In the US depth, we had to unitize the abstract notion of money into some physical notes, and in the solar system's example, we had to scale down the planets by a considerable factor in order to actually be able to see them. This effectively breaks the connection between the visualization and the ground truth, and is perhaps the biggest challenge of the technique. That is not to say that no value can be provided, however. For example, many participants still said that they gained a strong appreciation of just how much money the US depth is, which may ultimately be the desired goal in the first place. In summary, data visualization is a technique which can be used to help communicate the ground truth of the data. While the types of data most suitable to this are limited, data visualization can still be used to provide users a good sense of scale and appreciation about the data. We see these experiences as being complementary to data visualization, however, as data visualization can provide the quantitative understanding in the form of numbers, trends, etc., while data visualization can provide the qualitative understanding of the data's ground truth. In the future, it will be good to more formally evaluate the effectiveness of data visualization, as well as to explore how they may fit in the context of a broader narrative visualization. Finally, while we focus on VR in this work, the same concept can be applied to technologies beyond VR, such as the use of augmented reality, haptic simulation, and even olfactory devices. We hope that this work will spawn both future experiences for understanding data, as well as a deeper investigation into how to best create and more formally evaluate these experiences. Thank you for listening.
All right, thanks for a great talk. There have been a number of questions on the Discord about exactly what do you mean by the use of the word ground truth here. Could you clarify that?
Yeah, so what we mean by the ground truth is that when you have physical phenomena, so like things moving, in the examples that we use, people moving, buildings, such like that, you typically extract a certain amount of numerical data from that. So that oftentimes kind of translates this physical object or thing, or yeah, I guess ground truth, into some sort of number. So what we mean is to bring back that original understanding of actually seeing what it originally represents in the real world and kind of facilitating that knowledge to the user. I think this is kind of similar to the other question, which I'm going to answer right now, about the really abstract data with Tisney and abstract values and everything like that. That's something that we completely acknowledge, that a lot of the examples that we gave were very much built on data from physical values or phenomena, so things that have a very concrete real-world equivalent. It's, of course, going to be a question of whether or not these techniques can be used to represent, like you said, very truly abstract data. The kind of naive approach would be to map them with things of physical quantities, such that, say, mapping data to speed or motion or angular rotation, stuff like that. But at that point, I feel it's getting to a bit more closer to either standard immersive analytics or even data physicalization. So it's a bit of a fuzzy boundary at that point, I feel, but that's would be an open question, absolutely.
And one more question, where does the notion of visceralization meet or differ from the notions of immersion and presence as traditionally defined by VR?
So I think it's going to be a matter of whether or not, that's a good point. I feel they're both interlinked. So in the context of immersion presence, you obviously need that for the user to properly feel like the things that they're seeing or the world that they're in is actually, well, quote unquote, real or feels real to them. Yeah, it's hard to say. I feel like they're quite interlinked with each other, but yeah.
Okay. Okay.
Sorry for not being able to give a concrete answer.
No, that's great. So a lot of other great questions and comments in the chat, which you can have a look at. But now we will move on to our next paper to keep things going. We've got insights from experiments with rigor in an EvoBio design study presented by Jen Rogers.
Hi, my name is Jen, and I'm going to tell you about our design study we conducted with evolutionary biologists from the University of Idaho. These biologists work with complex phylogenetic tree data to answer questions about the diversity of life on Earth. We built a tool to visualize their data and iteratively refined the tool through user feedback. We conducted a case study too.
Jen, stop. I don't think that's a talk we should give. You should definitely give the other one.
Okay, sounds good. This talk is about a rich, diverse set of contributions that emerged from our experiments of treating design study as a method of inquiry and focusing on ways to achieve rigor when doing so. We grounded our research in the new interpretivist design study perspective that Meyer and Dykes presented at VIS last year. As a rejection of the software-centric view of traditional design study, this interpretivist perspective embraces a messy, subjective, design-oriented view, emphasizing the broad types of learning that can come from it, from insights about our design processes to insights about people's relationship with their data. This perspective is anchored in 6 criteria for rigor: informed, reflexive, abundant, plausible, resonant, and transparent. They give researchers a different way to think about design studies and what we can learn from them. We adopted this perspective in our design study, using it as a method of inquiry. We focused on 3 of these criteria: reflexive, abundant, and transparent, and experimented with methods to meet these criteria in our work. The result was a diverse set of contributions. We had 2 new techniques for visualizing multivariate trees with uncertainty, 2 experimental writing techniques for reporting on design study. We embedded a mini design study paper within a methods paper, and had direct linking in the paper to artifacts from the design study. And we had 3 methodological insights for conducting an interpretive design study: on reflective practices, on recording, reflecting, and reporting with research artifacts, and thoughts on assessing evidence of rigor. In the rest of this talk, I'm going to tell you about some of the ways we adopted this new interpretivist perspective of design study, and tell you about some of the exciting things that came out of doing so. Our design study had 3 main phases of research. The first phase consisted of an immersive field study at the University of Idaho, where I embedded myself in the lab of our collaborators for 3 months. During this phase, I was able to acquire a deep understanding of how our collaborators think about and work with their data. The second phase focused on iterative design of new visualization techniques, and we developed a tool for the lab we call Trevo. This phase was conducted mostly in my home lab at the University of Utah, but did include several trips back to the University of Idaho for in-person evaluations of the tool. The final reflection phase began as we started to develop ideas for reporting our design study and continued through the design of this talk. What made this design study different from others was our purposeful and systematic consideration of 3 criteria throughout our research process. We chose to focus on reflexive, abundant, and transparent due to their actionability and our own research interests. The ways in which we focused on them, I'm going to tell you about now. The first criteria we experimented with was reflexive, which encourages researchers to explicitly reflect on how they influence the research and how the research influences them. During this study, especially during the 3-month field study, I took regular reflexive memos documenting my insecurities and biases that could potentially have an effect on the research. Examples of these included: directing conversation during a meeting is hard for me. I put up emotional barriers when I am nervous, and I have a tendency of shutting down. I have not been recording these interviews as I am in the first week and I do not want to be intrusive. Reflexive notes really helped me understand the limitations in the ways I was conducting research and allowed me to make productive changes to the methods I was using. The second criteria we focused on was abundant, which calls for a design study to have rich details, many considerations and designs, and significant time in the field. We focused on abundance in multiple ways, including through our immersive field study, where we attempted to establish a long-term, deep engagement with collaborators as emphasized in Hall and colleagues' Design by Immersion paper. As a piece of evidence for abundance here, this was the community whiteboard in the Harmon lab. Once you officially became a part of the lab, you had your astrological sign and Enneagram personality number put up on the board. If you're curious, mine is here. A critical way we experimented with this criteria was building an abundant collection of diverse artifacts. We attempted to record everything. We collected a broad variety of artifacts along the way, including sketches, memos, diagrams, prototypes, email correspondence, text messages, photos of whiteboard doodles, related work, and paper drafts. At the conclusion of this study, we ended up with 170 individual artifacts. The final criteria we chose to focus on was transparent. This criteria argues that judgments about the quality of the research need to be made in the context of what was done, how it was done, and why it was done. Transparent reporting of design studies invites this scrutiny. Part of our motivation for creating an abundant collection of artifacts was to be able to transparently report on our process. Building on this collection, one of the ways we sought to support transparency was by explicitly linking to evidence from within our paper. For example, you can click on this linked reference to a text message conversation, and it pulls up a digitized version of the artifact in the browser. The second thing we did with our abundant artifact collection to support transparency was to build an audit trail as a companion to the paper. We developed a web-based interactive timeline where artifacts are represented as clickable squares. Clicking on a square pops up the digitized artifact on the right. This audit trail allows for tracing of our design study inquiry from beginning to end. As we were building our audit trail for reporting on the design study, it became an unexpected internal research tool as well. The act of organizing our artifacts into a timeline spurred us to reflect on our design iterations, leading us to make further changes to our visualizations. This reflection was aided by a tagging system we had implemented for our artifacts, which captures high-level concepts related to the artifact, such as design study method employed in the creation of the artifact, or the biological concept it is related to, for example, convergence here. This tagging system allowed us to trace the progress of concepts across the design study. Our website transformed into a tool that supported more than transparent reporting. It was also serving a vital role for recording and reflecting within the design study itself. This transformation led to a core methodological insight for us, which we formalized into a concept we call trace. Trace is a construct that supports tracing a design study from multiple perspectives over an abundant collection of artifacts. A trace can support tracing the design study temporally for reporting, as well as conceptually for reflecting. The capital R's represent 3 core research tasks that trace should support that are critical for design study. Recording abundant collection of diverse research artifacts. Reflecting on conceptual developments throughout the design study. And transparently reporting on the design study process. Trace has theoretical links to material traces. Here, the emphasis isn't on supplying dumps of evidence. The emphasis is on the ability to trace pathways from the evidence. Trace is also related to audit trails, which emphasize temporal tracing, as well as annotated portfolios, which focus on concepts embedded in artifacts. Our work is a first step towards theorizing about design study traces. We speculate that positioning the needs and goals of design study against these existing theoretical constructs could lead to further insight into the potential for traces to support rich, transparent design study. Trace was exciting, but there were two other methodological insights as well. Systematic reflective practices demonstrably benefited the research and design. And rigor comes from evidence, not just methods. Please see the paper for more details on these. So where do we go from here? And what could we learn from design studies? Interpretivist design study was meant to inspire the community to seek out richer and more varied insights from design study than just tools and techniques. Our work serves as a validation that this can in fact happen. The result of our interpretivist design study were 7 different contributions that included new visualization techniques, new writing devices, and methodological insights. We believe that interpretivist design study provides rich opportunities for learning, but how to do this well is still an open question. And what is the role of trace? Trace is one of the more exciting ideas that came out of our design study, and we've only begun to think about what this is as a construct, as well as our implementation of a trace as a website. What might a design study trace mean for supplementary materials, for open science, for design-oriented visualization research more broadly? We've only scratched the surface of these investigations, and we hope that our work serves as an inspiration for the community to embrace new ways of thinking about and using design studies, and to continue experimenting in this space. And with that, I say thank you.
All right, thank you for waking everybody up and getting all of us on the edge of our seats, both with presentation and with some pretty spectacular content. So a lot of interests in this abundance of data and this trace audit trail stuff. One question, how would this, can you reflect about how this abundance of data would work in an emergency situation like a pandemic?
That is a really good question. Thinking about it, one of the main problems, I think, or at least the difficulties, is that I think abundance is great everywhere, but the difficulty is what you know is important and then what you can actually do. So we really emphasized recording as much as we possibly could. And just on a surface level, I can see issues arising with like you're working with people's, I'm assuming, medical data. You have a very crunched amount of time, and you like have limited resources, basically. So I would say this might be a little more applicable to a retrospective understanding as opposed to in the emergency situation, if that makes sense.
Yeah, and a related question, can you reflect about how it ties in with our previous discussion on the desire of such artifacts in humanities VIS for trust building?
Yes, so this interpretivist perspective is really a way of accepting that there's bias in the data that we're collecting or the subjective nature of visualization design. I would say, for just contrasting it with or how it relates to humanities and trust building, the transparency and abundance of like curated into an auditable, I want to say audit trail because that was our initial intention, but just like a presentation that someone from an outside party could inspect, I think is very important for trust building, especially when you're working in this subjective, just the subjective nature of it. So I would say they complement each other well. And I would say that transparency of this process and emphasis, or I guess externalizing the subjectivity, is vital for trust building.
And does Trace make a distinction between divergent design artifacts and convergent evaluation artifacts? Question from Sean McKenna.
That is a really good question. So we're still developing Trace. Moving forward, we're really focusing on the reporting aspect of it. So you can trace by concept, you can trace by time, but it could be better, and we want to make it better. And I think divergence or convergence in design and development is a really interesting thing to incorporate in the, not, I guess trace is a construct, but the reporting of the trace of a design study. So yeah, I'll definitely consider that in our future work.
Super rich discussion in the chat, all kinds of people chiming in about how they love a lot of these ideas, but we have to move on. So thank you so very much. And we are now going on to a paper on a design space of vision science methods for visualization research presented by Madison Elliott.
And today I'll be discussing our paper called A Design Space of Vision Science Methods for Visualization Research. I'm going to show you a toolkit that will help you think about and test your visualizations as experimental stimuli. This is work that I did with Christy Nelthofer, Cindy Zhang, and Danielle Safer, who are all members of the VIS Vision Organizing Committee. To start, I'd like to introduce the research domain of vision science. As a concise definition, vision science is the study of how vision works and how it is used in day-to-day life. Vision science includes the study of visual attention, or where people look in a visual display, the study of visual memory, or how we remember information and then how we retrieve that information later, as well as the study of visual intelligence, which includes how we use visual perception and cognition to learn and analyze information. So, vision science is the empirical study of human visual perception, which happens to be the primary sensory system that we use to interact with data visualizations. It makes sense that vision science research methods have proved useful for answering both basic science questions about the nature of perception itself, as well as applied questions about real-world scenes and images, like information visualizations. Indeed, the study of human visual perception is a very mature domain of psychology research. It contains a rich suite of methodological tools and approaches that have been tested and refined for more than 200 years. This is also a research area in which our paper's authors were either formally trained or deeply involved with through collaborative work. The field of visualization has been increasingly interested in adapting methods from vision science to study, understand, and improve their visualizations. And we've had some good success at this. In what is now a classic paper, Cleveland and McGill explored how the visual system detects, assembles, and estimates data, providing empirically based foundational guidelines for the design of modern graphical displays. And more recently, work from Danielle Safer used classic psychophysics tasks to study color perception in common visual encodings, offering us new guidelines for graphical design that highlight the importance of mark size and color visualizations. And these are just two popular examples of what is becoming a budding area of interdisciplinary work between vision scientists and visualization researchers. The future of this collaborative effort between vision science and visualization is bright. There are an increasing number of perception-focused or perception-friendly workshops, such as Believe, ET-Viz, and VIS Vision, which even features conference events at both VIS as well as perception venues like the Vision Sciences Society's annual meeting. But despite its growing popularity, we still have a long way to go with this collaborative work. Although researchers from visualization are asking increasingly interesting and important perceptual questions, vision scientists and visualization researchers still do not share a common lexicon or vocabulary to easily facilitate their research partnerships. This stifles opportunities for communication and collaboration, and it also silos experimental knowledge. While there has been a notable rise in applied vision science research, many academics from psychology remain totally unaware of venues like IEEE VIS or Chi and have no connections with visualization experts. At VisX Vision, we have been working hard to facilitate better communication between these two groups through workshops, meetups, and other conference events. And recently, we became interested in creating materials to engage researchers from both domains. It turns out that no handbook or manual existed to document perception research methods for visualization or other applied fields. And as I mentioned, this really limits the practical potential for visualization researchers to work with vision scientists. So we took the first step towards fixing this problem with our paper. Drawing on our backgrounds and training in perceptual psychology, we curated a design space of the available vision science research methods that can be used in visualization research. Our paper presents readers with a comprehensive toolkit of empirical methods for conducting perception research to evaluate, test, and understand your visualization designs. We show you how to think about presenting visualizations as experimental stimuli in order to explore and measure your viewer interactions and ultimately evaluate your design choices. We break down the structure of experiment planning into 4 useful categories. The first category is paradigms, meaning the task that the viewer completes as they interact with a visual display. The second is adjustment types, meaning the way that the levels of a stimulus, as in the visual encoding of interest, are adjusted within and across trials in your task. The third is response types, or the manner in which viewers respond to or interact with your trial stimuli. And finally, we have dependent measures, or the desired data outcome that will describe viewer behavior and can be used in your statistical analysis. Our paper is useful for researchers who are asking applied questions with the hope of developing empirically supported design guidelines. And it's also useful for researchers who have questions about the nature of human visual perception itself in data displays. Overall, the goal of our work, and our most important contribution, is its ability to facilitate the planning and execution of rigorous, novel visualization experiments and tasks. We provide a methodological toolkit that will directly help researchers ask and answer important empirical questions for visualizations. For instance, this researcher might want to know how much lighter does one set of scatterplot points need to be in order for it to be distinguishable from the other set of points. A small difference in luminance may be relatively easy to perceive between 2 darker sets of dots. But the very same difference in luminance between 2 lighter sets of dots might be very difficult to perceive. With our paper, researchers can investigate these types of issues further, and they can start by choosing the right viewer paradigm or task. Since our example research question is asking about the appropriate difference in lightness values between these correlation populations, a discrimination task would likely be the appropriate choice. One way to perform a discrimination task is to have viewers compare dot clouds in side-by-side scatterplots. Here, you would ask participants which scatterplot is showing the lighter dots. In this case, the viewer should indicate that the scatterplot on the left has lighter dots. But our design space will help researchers consider other possibilities as well. For instance, the researcher might prefer viewers to discriminate the luminance of 2 populations in the same scatterplot. It's really just a matter of matching the right paradigm to whatever your real-world task and basic research questions are. In this example, you might be interested in how similar you can make the luminance of 2 dot clouds before viewers can distinguish them. Once your task is decided, researchers can choose how to adjust the stimuli across trials. In other words, they can decide how to change what people are seeing over time as they complete the experiment. It's important to think about stimuli adjustments because we want to capture the full range of viewer behavior at different levels of our stimuli. Think different encoding possibilities for your design. In our single scatterplot task, the viewer needs to decide when they can see 2 populations of data on the chart. The researcher might choose to apply the method of limits, where the dot luminance of one population is slowly adjusted until the viewer indicates that they can detect a second population. Let's do that again so you can play along. Go ahead and watch the dots change to see when you notice the second population appear. Great. This response indicates the detectable luminance or lightness difference between these dot populations. And again, our design space is going to show you plausible alternatives at every stage of planning. So for the side-by-side discrimination task, where viewers have to decide which scatter plot has the lighter dots, here in this task, researchers might choose to apply an adaptive psychometric procedure. You can play along on the next few slides for this demo, each time deciding which side you think is showing the lighter set of dots. An appropriate adaptive psychometric procedure for this instance would be a staircase algorithm. Staircase algorithms work by making the task harder or pushing the luminance values of the dot populations closer together after each correct viewer response. This goes on for many trials. And in this demo, the screen on the right is showing you example trials or example tasks, and the chart on the left is plotting correct and incorrect participant responses along the way. So participants keep going, and as they keep making correct responses, the stimuli levels move closer together. This goes on until the viewer makes an incorrect response. After each incorrect trial, the task is made easier and the stimuli levels are pushed further away from each other. This pattern continues, and participants do their best to make these discrimination judgments. Note that there will be more response variability near the viewer's perceptual discrimination threshold, and eventually the participant will reach what's called a steady state accuracy, where they can reliably tell the difference between the two luminance values in the dots in these plots. It's up to the researcher to set the details of this steady state accuracy calculation, and references and tips are provided in our paper. So, once the researcher has their task and stimuli adjustment decided, they can then pick the viewer response type. Our paper helps readers consider when to use all of the various options that exist. In our single scatterplot experiment, viewers could respond by indicating a stimulus level. Here, that means indicating the luminance level at which the second set of scatterplot points is detectable. Viewers could do this by pressing a spacebar when they first notice that second population or notice that lightness difference. For our side-by-side scatterplot discrimination task, a 2 alternative force choice response would be a good option. Researchers could program their task to take keyboard responses that map to either the right plot or the left plot. And once your response type is decided on, the final consideration for an experiment is the dependent measure of interest. The dependent measure is an important consideration in terms of ensuring that the right perceptual signal is being detected. Dependent measures are the behavioral data points of interest in your experiment, and it's critical to plan these alongside the experiment's statistical data analysis. In our side-by-side scatterplot task, each luminance level that we test will yield a just noticeable difference threshold called a JND. This is the difference in lightness that makes a perceptual difference to the viewer. Researchers often plot these JNDs against their corresponding lightness levels. This measure helps us model and understand viewers' perceptual precision at each level of luminance in the scatterplot design. This kind of modeling is how we describe and measure performance in vision research, and using this approach can help visualization researchers build rigorous design rules that are supported with computational evidence. These examples are just a small subset of the ideas that are made possible with our design space. But we sifted through all of the behavioral research choices available in vision science to produce a comprehensive catalog of choices that you can use to design awesome, complete experiments with the 4 categories or stages that we've just outlined. We included lots of helpful figures, and I promise they'll be even more helpful in the paper itself. We illustrated each potential option at every stage of the design space. All of this is to say, go read this paper. It will help you do good science. And in summary, our design space has 4 main contributions. The first is that it will help visualization researchers read and understand the methods used in perception papers. Hopefully this will inspire more thorough background review and empower new researchers to dig into the vision science literature. It will help researchers design rigorous empirical tasks to answer their questions. There are so many more possibilities than simple discrimination tasks. And if you don't believe me now, check out our list of 11 paradigms that you can use to study scatterplots with. It's in the paper. Once armed with these awesome new tasks, It will enable researchers, even curious perception researchers, to create and evaluate new design guidelines for visualizations. And finally, our design space of research methods will help researchers discover how human perception works in informations, visualizations, and data displays. This is an area ripe for more interdisciplinary collaborations, and we hope that providing a common lexicon will help kickstart some powerful conversations across fields and bring new researchers into this valuable space. And hey, we mean it. We really hope you check out our paper and get inspired to do some cool work of your own. Before I conclude this talk, I'd also like to invite our listeners to join the VisX Vision community. We'd love to have you participate in future workshops and conference events to meet and collaborate with like-minded scientists. Joining VisX Vision is a great way to connect with others, to discuss how to use the elements of this paper in more detail, and even get feedback on your own experiment ideas. Lastly, I'd like to express many thanks to the VisX Vision organizers and our group of affiliates. We couldn't do this without you guys, and we are so grateful for our community. I hope you have a fantastic conference and that I hear from you soon at Virtual Viz. Thanks.
All right, another fantastic talk in this session. So Madison, thanks very much. There was a question, can you elaborate a bit on how the term visual intelligence might relate to what we call spatial intelligence and cognition, from Vande Tamara?
Yeah, that's a great question, and I could elaborate on that question for literally hours, probably. I'm basically talking about both of those concepts when I refer to visual intelligence for the purposes of this talk, but those are definitions that are empirically debated in the vision research community all the time. But yeah, for the purpose of this conversation, I think it's fair to say that visual intelligence encompasses both of those ideas.
And does your design space try to address the impact of different hardware like screens and monitors as well as environmental factors on physics experiments?
So we don't cover those kinds of issues in this paper specifically. We did sign a book deal, so we'll be releasing a much longer handbook next year where we probably will touch on some of those issues. It's a great point, and it's definitely very important to consider when you are designing visual tasks.
Yes, I'm super excited about that book. It'll be in the CRC Press Viz series that I edit, so I'm particularly excited about that one. So stay tuned for that. There will be even more fantastic methods things. So lots of great reactions in the chats. People being enthusiastic about this. In the interest of time, I am going to move on to the next one. So thank you so much, Madison, and you can do more engagement in the Discord. And we will now roll a structured review of data management technology for interactive visualization and analysis presented by Carlos Scheidegger.
Thank you for tuning in. This is a structured review of data management technology for interactive visualization and analysis. I'm Carlos Scheidegger from the University of Arizona, and Leilani Battle is my co-author at the University of Maryland. That link there goes to a website where you can get the paper and other things like our full bibliography with metadata. As you listen to this, I hope you're safe and comfortable. I'm recording this talk in September of 2020, and this is currently smack in the middle of the COVID-19 pandemic. I'm literally locked inside a closet full of pillows as we're recording this, and we're locked all inside our houses. So I truly wish I was giving this talk in Salt Lake City and seeing all of you. We really miss you all. So what is this paper about? Leilani and I both work at the intersection of data management and interactive viz, and this is our attempt to summarize some of what we learned along the way. The main result of the paper is a structured literature review aimed at both developers and researchers in the field. We use two axes to categorize the papers we include. The first axis describes the optimization strategies developed in the paper. In the second axis, which viz tasks are supported by the technique. This two-axis categorization is important to us. We want to be able to discuss the implementation techniques that we found in the papers without forgetting the big lessons in visualization design. Implementation techniques don't exist in a vacuum. They serve the user who is trying to achieve something using our interactive visualizations. So we wanted to make sure that both axes captured these aspects. So, what concretely will you find in our review? We collected publications from the big database and VIS venues going back to at least 2000. We chose the range of publications to include sort of arbitrarily, but we think it gives good coverage. Each of us read the title and abstract of every paper looking for optimization technique descriptions. We arrived at 6 different topics, which we'll talk about later. But first, let me tell you about some of the limitations of this survey. First, we focus on tabular data. There are important questions about databases in VIS for non-tabular data like graphs, text, or images. We really don't go into these because of space. Second, our coverage is not exhaustive. We use the biggest venues in databases, VIS and HCI, as a proxy for community interest. This lets us, for example, use paper counts later as a rough measure of community activity around the topics that we're going to talk about. But importantly, don't use the survey to see who did what first. Comprehensive search tools like Google Scholar are more suited for those tasks. Then, we independently read the 278 papers we first found and labeled them. We used the database codes we got from the abstracts, and a small simplification of the typology from Matt Bremer and Tamara Munzner. After many weeks of meetings and discussion, we eventually arrived at 130 papers which were labeled consistently on these 2 axes that I'm going to tell you about. But before we go further, let me tell you another limitation of this survey, which is that by design, we wanted to describe existing work. In other words, this is not a vision paper. If a vision paper is really what you're looking for, and I promise you, Leilani didn't make me say this, I really like the vision and position papers that she has written, so you really should go read those. The task axis is represented as rows in our main reference table, and there are 11 of them. They are encode, select, navigate, arrange, change, filter, aggregate, annotate, derive, record, and import. We have a full description of these interaction types in the accompanying website. The second axis we use is the optimization axis, or the database techniques. We represent this in our table as columns, and there are 6 of them. In the paper, we have a short description of each of these techniques in case you're not familiar with them. But here in this talk, I want to go into detail about one of them so you can get an idea for what they look like. And this is the idea of provenance-based techniques. Provenance means, roughly, the tracking of origins of things as they are made. This can mean, say, keeping track of which rows in a table are responsible for a query result being a certain value. Here's one example publication in our survey. Salidas and Wu designed a system called Smoke that was presented in VLDB 2018. Smoke shows how physical query planners in databases can be written to make provenance queries faster. In fact, in Smoke, these queries are fast enough to drive interactive visualizations and their low latency constraints. In our categorization, Smoke supports the select and aggregate interactions and uses indexing and provenance optimization techniques. Now let me give you a bit more context about our categorization. There are many papers about provenance in visualization, and there are many papers about provenance in databases. As you can see in our next slide, though, we found, surprisingly, that provenance is not a very popular way to make interactive visualizations more efficient. Once again, the rows are the interaction types, and the columns are the optimization strategies used by the database system. As you can see here, by comparing the different rows and columns, this organization can help bring attention to underexplored areas like the case of Smoke. In this table, a reference can appear in many cells, and the cells are color-coded by the number of references in them. Using Smoke as an example again, it appears in 4 separate cells, since it has 2 interaction task tags and 2 optimization tags. Our paper describes our analysis of the results in detail, but here are some of the things we learned for you to take away. The density of references in each cell, that is, how many papers it has, sort of matches the maturity of the subfield and the kind of work that tends to appear in those papers. Orange cells have 10 or fewer references and tend to contain work that highlights observations and opportunities, often through use cases where novel optimizations are necessary or possible. Green cells have between 10 and 19 references, and we found those cells to tend to contain work formalizing those optimization opportunities. In the blue cells, which have 20 or more references, we start to see work developing more general systems. We hope this talk gives you an idea of the work and you will want to go read the paper. But if you don't have the time to do so, here are main takeaways from the reviewer and analysis. For cases where systems are being built, we think that the monolithic DB approach of building one big system is hurting adoptance by visualization practitioners. It would be useful to have access to optimization techniques as composable building blocks instead. Where algorithms are being developed, we think it's important to get the fundamentals right. Theory and models have served the DB community particularly well, and we can't help but wonder what the situation in VIS could be like. Finally, where optimization opportunities are just beginning to appear, we think it's important to have the ability to compare different approaches, and this is where community-supported benchmarks can shine. So that's our structured review of database techniques for interactive visualization and analysis. We want to thank the NSF for the support, and we want to thank you for listening. If you want to see more, please visit that website.
Okay. Thanks, Carlos and Leilani. That was an immense labor of, what was that, 278 papers read? Well done. Everyone is impressed by that on the chat. I have a question. I don't know that you got into it in the talk, but in the paper when I read it, you said there was this gap in the intersection between data ingestion and interactive visual analytics. And I'm curious, do you think of data wrangling as fitting exactly into that gap? Because that seems like at least there has been some attention in that area.
That's a really good question. So Leilani and I were very explicitly taking a performance-centric perspective on this. And so in that sense, I completely agree with you that there's a lot of really good work done on sort of how to do data wrangling. I mean, the entirety of Trifecta is sort of how to like connect data wrangling and sort of interactive viz and all of those things that come into play. What we were trying to characterize are things that sort of prevent the interactions from working at like the scale of data that we tend to see. And in that sense, sort of the cold start problem is really serious, which is, you know, you have this big data set and you want to start playing with it right away. What can you possibly do? So that's the way in which we think we saw the gap. And in that case, I do think that there's something to be said about the fact that data wrangling does assume that you can just run whatever cleaning script you have over the entire data set, and you're not going to have problems with that. So I wonder if that's one way that you can sort of try to find something that has to do with data wrangling. But the other thing is we also assume that the data was tabular and clean to begin with to make our characterization tractable. And that's another way in which it's not really, like, it might not be realistic.
Got it. Another quick question. I noticed in the paper you mentioned supplemental material, but I couldn't figure out where it was.
Yeah.
Is that something maybe you could put a link to?
I'll post it on Discord right now. Yep.
Okay.
Give me 1 second. I have a window open right here. So the link is here. Great. I posted it on Discord, and there's a link there to the paper, to the actual bib file, and you can search for terms and sort of. I didn't have time to actually put viz on this, so shame on me for. But
no
this should have charts in actually, like, it will be there soon. So it's a few commits from being there, but at least you can navigate the bib as it is.
Fantastic. There is no shame. You read 280 papers in depth. Any other questions for Carlos in the chat? I am trying to scan for that.
Danielle asked a question about how to characterize, how to draw on these efforts.
Thank you.
So Danielle Zephyr asks, how might we draw on these efforts to characterize what makes a good benchmark? We go into detail a bit on that on the paper, on how we think that sort of good benchmarks should be there. And from, again, sort of our systems and implementation centric perspective, we think that a feature of a good benchmark is that it's not confined to the specific technique that you are presenting on your paper, that it sort of should be generalizable, so that results from other papers should be sort of in a uniform format, so people can combine them one another. And that in some sense, we should have sort of a way to go from like data collection to system building to evaluation to posting the results in like a uniform format, which doesn't quite exist for a lot of the things that we talk about. But I think that's a good way to make it so that the community can all build on these benchmarks.
Great. I think unless another message sneaks in the next 10 nanoseconds or so, what we will do is declare victory with an amazing set of talks, an amazing set of chats from both the audience and the authors. There's been a lot of great back and forth. So I would like to thank everyone for making this a thought-provoking session. I think one of the chat messages was said, how do we know it's a good conference? I have so much homework from Adriana. So totally agree with that. So much to learn and do. Thank you all. And we will now move on to break, and then we will have a final wrap up of VIS. Thank you.